Today I want to focus on projectile motion, and I've got a few model rocket clips on YouTube. And I was always interested in the mechanics behind how it worked. And now that I've taken some physics, I can show you guys today the physics behind how projectiles move. So projectile motion. Before we start, I just have a disclaimer that I want to say, and that is we're assuming that this is in an isolated system. All these questions are in an isolated system, so that means there's no friction and energy conservation is 100%. There's no air resistance, no heat, no energy loss due to friction, etc. So it's a little unrealistic, but this is as close as I can get. So let's take our first type of problem. Let's say that I've got a projectile. I'm standing in a field, and I've got a rifle. Hope the camera can see this. I've got a rifle, and I shoot a projectile straight up at an initial speed of, let's say, 335 meters per second. So what am I going to ask? I'm going to ask, how high will this go? So if we look on our sheet, on our formula sheet, which I don't have here, I've just memorized this one. It's a really useful one, and we can derive it using this formula. You guys see this? Hope so. That's sigma, sum of initial energy equals sum of final energy. We can derive a formula that goes like this. So this is final velocity. That's initial velocity, that's acceleration, and that's distance. And I can show you the derivation if you like, but that'll take a while. So let's list what we know here. We know that I don't have to break this down into x and y components, which we'll do later, because that's obviously a lot more complicated. So let's list all our variables. What are we given? Well, we know initial velocity is given here, 335 meters per second. What's VF? Let's think about this, because we are given VF. If I shoot something in the air for the slightest amount of time, the velocity is zero because it's hit its apogee. It's hit the point where there's no more kinetic energy left. It's all potential energy. So VF is 0 meters per second. Because think about it, if you were to throw a football up in the air for, I don't know, a tenth of a second or something, it would remain stationary in the air because all of the kinetic energy, well, almost all, because this isn't an isolated system, almost all would be converted into gravitational potential energy, so it wouldn't be moving. But for, like I said, for this we're assuming it's an isolated system. So we know VF is 0 meters per second. Acceleration. Well, acceleration due to gravity on Earth is 9.81 meters per second squared. So what is it here? Well, I'm shooting it up in the air, so it's negative 9.81 meters per second squared. Distance, that's what we're looking for. And we don't know that. Time, we don't know that either, but I can show you later. So let's take our formula here. Let's write VF squared equals VI squared plus 2AD. And what are we solving for? Well, we're solving for distance. So isolate for distance. That's the way I like to do it. So if we do that, we get VF squared minus VI squared over 2A equals distance. And when you plug that in, which I've already done here, you get an altitude of 5,719 meters. So that's vertically launched projectiles. So this would hit an apogee of 5.72 kilometers. And that's vertically launched. Okay, let's do something a little more complex. Now, it's really not that bad, and I know 3 ways you can solve this. I'll show you guys 2. The 3 ways are: 1, a differential equation, which I'm too lazy to show you today because I need to do background stuff. I can use energy conservation, so that's what we had up here. And I can do kinematics. And I'll show you guys kinematics and energy conservation. And if this doesn't make any sense to you, I'm just winging this, so I'm sorry. Okay, so let's do a freely falling object. So let's say I'm standing on the Calgary Tower, which is about 191 meters in elevation, or height, whatever. And my drawing skills are amazing if you don't already know. Let's say I'm standing there and I've got a penny in my hand. And I drop the penny from 191 meters, and it's allowed to freely fall until it hits the ground. How fast will it be falling when it hits the ground? That's a freely falling object. So I'll show you guys the easiest way. Let's go back to our great formula here. That one. Love that formula. Let's just plug it right in. Well, first let's write down our givens here. All we know VI is 0 meters per second. VF is what we're looking for. That's what we're looking for. Acceleration is positive 9.81 meters per second squared, because it's falling down, it's not being tossed up. Distance is 191 meters. Time, we have no idea, but we don't need time. Let's use kinematics here. Let's say VF squared equals VI squared plus 2AD. That's kinematics. We're looking for VF, so VF is the square root of VI squared plus 2AD. But VI squared is 0 meters per second, so we can just get rid of that. So what we've concluded is VF is the square root of 2AD. And we're given both A and D. So we can just plug it right in. And it should be around 61 meters per second, I think. So VF is the square root of 2 times 9.81. And make sure you always include your units. And distance is 191 meters. And we can just plug that right into here. So if I do that really quick, you get 61.2 meters per second. So that's how fast it'll be falling the very moment it hits the ground. That's kinematics. Let's use energy conservation. It's a little more convoluted, but it still works. And if you want to convert that to kilometers per hour, you multiply by 3.6. And if you want to convert kilometers an hour to meters per second, you divide by 3.6. Now I need a new piece. Okay, let's do energy conservation. So let's say that, just give me a sec here. Yeah, let's do energy conservation. Let's say that sum of initial energy, that's a horrible sigma, oh well, equals sum of final energy. Which makes sense because it should have as much gravitational potential energy as it does kinetic energy. Because the first law of thermodynamics is the amount of energy in the universe remains constant. So let's break this down. Let's say that initial potential energy plus initial kinetic energy equals final potential energy plus final kinetic energy. We can get rid of 2 to start with. It has no kinetic energy at the top because it's sitting still. It's full of gravitational potential energy. So we can get rid of that right away. And there's no potential energy at the bottom because it's been all converted into kinetic energy. So we're left with these 2. Now what kind of potential energy does it have? Well, it's above Earth, so it'll have gravitational potential energy. And if you look on your formula sheet, that's equivalent to mgh, mass times acceleration due to gravity, times the height above the ground. So mgh equals the kinetic energy formula, which is 1/2 mv squared. Mass times velocity squared over 2 is another way to say it. This is where we start. So what we're looking for, this is where we start to rearrange stuff. What we're looking for is V, obviously. So we can get rid of m right away, and if we multiply both sides by 2, we get 2gh equals v squared. So what's v? Well, v is the square root of 2gh, and that's exactly what we had over here. 2ad, 2gh, because g and a are the same in this case, and d and h are the same. So you can plug it right back in. You can say velocity is the square root of 2 times 9.81 times the height, so 61 meters per second. So that is freely falling. Now, how long will it take to hit the ground? Well, there's another kinematics formula, and it goes like this. So distance equals initial velocity times time plus 1/2 acceleration times time squared. And the other way you can write this is final velocity times time minus 1/2 at squared. So in this case we'll use this formula. So let's isolate for time. If we do that, we get time is the square root of 2 times distance over acceleration. I'm too lazy to show how you get that, I'm sorry. T equals the square root of 2d over a, and we've got d and a already. Both d and a is given in the question, so we can find time right away. It should be around 6.2 seconds, I think. So if we plug that in, we've got 2 times 191 over 9.81. Yeah, 6.2 seconds. And that's freely falling. Now, what if I were to throw the penny off of the Calgary Tower at a certain speed? Now, if you were to ask many people this question, what they would do is take our our VF and just add on the initial speed, but that doesn't actually work. What we need here is we need to go back to energy conservation. So let's just start from the top here. Let's say that sum of initial energy equals sum of final energy. And then we got to do this all again, I'm sorry. EPF is 0 because it's all kinetic energy, so we can get rid of that. So we can say EPI, initial potential energy, plus initial kinetic energy, because it does have kinetic energy initially because I throw it off at a certain speed, straight down, equals final kinetic energy. And now we expand this. So let's say mgh plus 1/2 mv squared equals 1/2 mv squared. So if we multiply by 2 and divide out m, then we get 2gh plus vi squared equals vf squared. Hope you guys saw that. Sorry. So VF, if you throw it off of something, is not VF plus your initial VI. It's a little more complicated than that. This is our final formula. And that always works as long as friction is ignored. So if I were to throw the penny at a speed of 20 meters per second, then I would just plug acceleration due to gravity, height, and initial speed, and that would give me the final speed. And that's freely falling objects. Okay, let's get a little more complicated here. Let's look at horizontally launched projectiles. So let's say I'm standing on a 10-meter high platform. And I started on it already just to save some time. And if you're wondering what that is, I had a little screw up, so. Let's say I'm standing on a 10-meter tall platform and I throw something off at a speed of 20 meters per second. How far will it land from the base of the 10-meter platform? So there's just one concept that I found interesting. Imagine that you and I are in some salt flat or something, and you've got a golf ball and I've got a hunting rifle. And at the exact same moment you release the golf ball, I fire a bullet out of the hunting rifle. And we're both at the exact same height that the gun barrel and the ball is released from. Which one will hit the ground first? Well, the answer is they'll hit the ground at the exact same time. So this is actually true, that it doesn't matter what the horizontal component of a projectile's velocity is. It'll hit the ground at the same time as if the velocity was 0. So if there was even a slight bit of vertical velocity, which we'll break down with trigonometry in just a minute, it would take longer to hit the ground. But here there's no vertical velocity. It's just one horizontal component, which is 20 meters per second. So all we need really to find this is the uniform motion equation, which I'll just zoom in here for. this is it right here. Distance equals velocity times time. That's a classic kinematics formula. So we know velocity is 20 meters per second. We don't know time, which we can find, and distance is what we're looking for. So we know Vx is like the x and y components. Vi is 20 meters per second. Dx, we don't know. That's dx, what we're looking for. Tx, how long will it take for this to hit the ground? Well, we can go back to the previous section and we can find that through this formula here, non-uniform motion, we can get time it takes for an object to hit the ground is this, rearranged. So, we can plug, we know these, we know the vertical distance is 10 meters, and we know acceleration is 9.81, so we can plug that directly in and say our time it takes to hit the ground is 1.42 seconds. And then we just go directly to our uniform motion. So we say that distance dx equals vx times t. Well, we know vx and t. We just figured out t. So we can just plug it directly in. We can just say dx equals 20 meters per second times 1.42 seconds. Well, it'd be 4.3 if I were to round it correctly, but oh well. Let's just plug that in. It would land 28 meters from the base. And that's all it is. We only really need two formulas to solve this. So if I were to say that this is 100 meters high and I throw it off of something, I throw something off at a speed of 30 meters per second, we would just plug those into here. So we'll say the time it takes is 2, the square root of 2 times 100 meters over 9.81, and we get our time. And then we just multiply it using our uniform motion equation. And that's a horizontally launched projectile. Let's work backwards now. Let's say that I'm on a platform and I've got a paintball gun. So let's say the platform is 4.7 meters high. And I'm up here. I'm up there and I fire a paintball at some unknown speed. Just down like that. If it lands 20.1 meters away, how fast would I have shot the paintball out of the gun? So all we know is I shot it at a height of 4.7 meters and it lands 20.1 meters from where I shot it. So let's go back to our non-uniform motion. Let's say distance equals VIT plus 1/2 AT squared. And if we isolate for time, we can figure out how long it'll take to hit the ground. Because like I said, the horizontal component of a projectile's velocity does not interfere with the time it'll take to hit the ground. So let's isolate for time. T equals this. And if I plug that in, I'll get a time of 0.978 seconds. Okay, that's something we need to know. Now let's list our uniform stuff. Uniform motion. We know v of x. Well, we don't know v of x. We know that's what we're looking for. So we don't know v of x. D of x, we do know. In the other question, we were looking for this. Now we're looking for this. We know d of x is 20.1 meters. And we just figured out t because tx and ty is the exact same thing. T is 0.978 seconds. So what can we figure out from here? Well, it's pretty simple. V of x is distance over time. Because remember, distance equals velocity times time. Correct? Okay. V of x is simply 20.1 meters over 0.978 seconds. So, what is V of x? Well, V of x is, I think, V of x is 20.53 meters per second. And that's how you do horizontally launched projectile questions. Okay, let's get a little more complicated. Let's say that I fire a projectile at an angle this time. So it's not perfectly vertical and it's not horizontal. Let's say it's at an angle. Let's say I fire a projectile at 18 meters per second at an angle of 40 degrees. Now let's look for its range. How far will it travel horizontally? Well, what I'm going to need to do here is break the velocity down into components. And since we're given an angle, we can find the horizontal and vertical components of its velocity, which is what we need. So if you were to study my diagram, you can see what we can do here is we can make a triangle out of the components of the velocity and the hypotenuse of the triangle. So we can say that this is the horizontal component, or Vx, and this is the vertical component, Vy, and we'll use that to solve the maximum height in just a minute here. So if I were to go to my trig ratios, sine, cosine, tangent, you'd see that cosine is adjacent over hypotenuse. That's what it's equivalent to. And if you're unfamiliar with basic trigonometry, I suggest you go watch a video on that first and then come back to this because it'll make a lot more sense to you. Cosine is adjacent over hypotenuse. Now we've got theta, which is 40 degrees, and we've got the hypotenuse, which is 18 meters per second. So I can say cosine theta times hypotenuse equals adjacent. So the cosine of 40 times 18 is 13.79 meters per second. So that's the horizontal component of this projectile's velocity, which is what we need. But we also need Vy, because think about it. D equals V times T. We're looking for D. We just figured out V, and now we need to find T using Vy. So it's, I guess, I'm hoping you know where I'm going here. We're going to use sine. We're going to say Vy equals the sine of 40 times 18 meters per second. So the vertical component of its velocity will be 11.57 meters per second. And here's where it gets interesting. We can find time using the vertical component of its velocity. We can say from our formula sheet, this is a pretty common formula, acceleration of anything equals Vf minus Vi over t. Correct? Now, we're looking for t, so what would we do here? We just say t equals Vf minus Vi over a. And we know the initial velocity, the initial vertical component is 11.57. What will the final be? Well, it'll be the same, but with a flipped sign. It'll be negative 11.57. So what we can do here is we can just find time really easily by saying VF is negative 11.57 minus 11.57 over A, which is in this case negative 9.81 because we're going up. And there's our time, 2.36 seconds. That's time. And what do we do here? We just go back to this formula. We say the distance is our horizontal component of our velocity. That's all we care about. We just look at the horizontal component. Velocity, so that was what, 13.79 meters per second times t, which we just figured out was 2.36 seconds. Because that's how long it'll be in the air for. So our distance will be around 32.5 meters. And that is how we solve range. Let's do another example here. Let's say that, let's say that I fire a projectile at an angle of, let me just zoom out here a bit. Let's say we fired at an angle of 53 degrees. Just like that. And let's say that my initial velocity is 20 meters per second. Now, like I said before, what we can do here, I'll just draw a trajectory here. What we can do here is break this down into a triangle. So we can say this is Vy, and this is Vx, and this is just V. Let's break this down. Let's say the sine of 53 times 20 meters per second gives us our vertical component, and that will be 15.9 meters per second. So that's our vertical component. Now let's find our horizontal component. And I forgot to say, we know sine is opposite over hypotenuse. And if we isolate for opposite, which is Vy in this case, we'll get the sine of 53 times 20 is Vy, or opposite. And same goes for cosine. Well, almost. Cosine is adjacent over hypotenuse. So let's find adjacent. Let's say the cosine of 53 times our hypotenuse, which is 20 meters per second, is our horizontal component. So that will be, I just got to calculate that one. That will be 12 meters per second. 12, pretty close to 12. Okay. Now we've got our x and y components of our velocity. So what can we use with that? Well, we can find, let's go a little lateral here. Let's find the maximum height. Let's find the apogee first. Let's say that, let's go back to our great formula. Let's say Vf squared equals Vi squared plus 2AD. So if you're confused here, I'm finding the maximum height. How high will this projectile go? Which I like to call H max. Well, that's a no-brainer. What we can say is distance is final velocity squared minus initial velocity squared over 2 times the acceleration. And we just plug it right in. We say, what is our vertical component of our velocity? Well, that'll be 15.9 meters per second. And what'll be our final? Well, our final is 0, because just think about it. This is the non-uniform motion part, because Vy changes as it goes up and down. Vx stays the same. We want to find the maximum height. So we look at our variables we have here, and we just say, okay, Vf, just give me a sec here. Our Vf is 0, correct? Now, subtract our Vi. What is our Vi? Well, I said it was 15.9. Hope you guys can see that. It was 15.9 meters per second, and we square that. And what's our acceleration? Well, it's 2 times negative 9.81, because we're heading up. Earth wants to pull this projectile back down, so it's negative 9.81. And we find that our maximum height will be around 12.8 meters. So dy is 12.8 meters. Now let's find our range, like I said before. What do we do for our range? Well, that's pretty easy. We find time. Here's another way to find time. I showed you guys using that other formula. Let's go back to my first formula. Let's say d equals VIT plus 1/2 AT squared. Time, if we rearrange that, will be equivalent to this. Just like that. And we know our d is 12.8 meters. So what we can do is plug that directly into our equation. We can, and then multiply by 2. And I'll show you in a minute here. The time it takes to hit the ground will be the same time it takes for it to reach its apogee. So we multiply by 2. So to find time, we simply plug in 2 times 12.8 over A, which is 9.81, positive in this case because we don't want negative time. And we multiply that by 2 because what we're finding with this calculation is the time it'll take for it to fall. And we multiply by 2 to find the time it'll take to hit the top. So if we do that, we get a time of 3.26 seconds, approximately. And then we just go back to our uniform motion equation. We say d equals v times t, and to find the range, we just plug in our horizontal component. So I said that was 12 meters per second. 12.03 to be exact. Well, more exact. 12 meters per second times 3.26 seconds. And that'll give me a range of approximately 39.2 meters. And that's how we do range and maximum height problems. So let's just recap what I said there, because it probably sounded pretty convoluted. If we want to find the range of a projectile, what you're going to have to do is break these into components, and you're going to have to find the horizontal component of the projectile's velocity. And we can solve time 2 ways. This is the harder way, obviously, because we need to know the maximum height. To find time, we can just use this formula. We can just say time, the time it is in the air for is just, we're just looking at our vertical component of our velocity, and we plug that into here because we know acceleration is Vf minus Vi over t. That's just common sense. Let's isolate for t. T is Vf minus Vi over A, since A is Vf minus Vi over t. That's the easier way to find time. All we do with these two is go back to our uniform motion. We know d is V times t. You just directly plug it in, that's all you do. Vx times t will give you dx because d equals V times t. That's how you find range. Let's find maximum height, or apogee. You're going to need the vertical component of its velocity because, like I said in our horizontal section, the horizontal component won't affect the time it takes to hit the ground or anything, or its height. So use the vertical component. Find Vy. Use the sine ratio to find Vy. And we found Vy. And then you just go back to my favorite formula, which we derived with energy conservation. Well, I didn't show you, but you can. This. And we just plug it into, well, we isolate for d, and then we just plug what we know in. And I remember I did derive it actually. Yeah, that's how we find max height. You just plug it directly in. And remember, when you reach the apogee, the final velocity will always be 0, because for just the slightest moment, just picture this. For the slightest moment, it's resting at 0 meters per second, and then it falls back down. So we can say Vf is 0 meters per second. And you just plug it in. That's all you do, and that's how you find H max, or apogee, or max height, whatever you like to call it. Okay guys, let's look at one more type of projectile motion problem. Let's say that I fire a projectile at 50 degrees to the horizontal. And I know the x and y components of its velocity. And I have a target 2.17 kilometers away, and it's 50 meters above the ground. What we want to do here is track the x and y positions at a certain point in time. And my notes are horrible on this, so I'll just explain it the best I can. I already calculated time. That's 23.43 seconds it's in the air. Now, what we need to do is we need to know the vertical displacement when our horizontal displacement is the length it is away from here and here, which in this case is 2,170 meters. Now, what do? Well, we just plug directly in. We've seen that formula before. This is our vertical component of our velocity, and we just find the vertical position when we know our horizontal position and time. Now, that's the time it was in the air for totally. Now, what's the time when it's at a distance of 2,170 meters? Well, to do that, we can just go directly to our uniform motion again. We can say d equals V times t, d of x equals V of x times t. Isolate for t. We know d of x is 2170, and we know V of x, which is, in this case, 96 meters per second. Let me just get that in focus. And we can find our time. So what is the time at which it has hit this? Well, in this case it's 22 seconds, 22.502. And you just go back to our formula. Now, I highlighted this. Make sure that if it's traveling up, it's negative. The acceleration due to gravity is negative. And you just plug it in. So you say the vertical component of its velocity is, which is in this case 114.924 meters per second. The time when we hit the target, 22.5 seconds. And this is just the rest of plugging it in. 1/2 times negative 9.81 meters per second squared times the time squared. And we can find our vertical distance when we know our horizontal distance. So in this case, our vertical displacement, so this component, is 102 meters. And obviously we missed the target because the target is 50 meters above the ground. So that's how you do projectile motion. Hope it helped.